I recently came across these hardware dongles and I wanted to know how they work. So naturally I took one apart. The only screws on this thing are these weird looking 3-bladed screws. And if you just search for 3-bladed screws, you find out they are called actually tri-wing screw. And you can find a bit set to undo them for about $10. So once we take the thing apart, we see that it's just a metal plate with some contacts soldered to it. My theory is that each dongle just represents a pattern of connected pins. So we could easily replicate such a dongle. This dongle has about exactly 30 holes. So you could do this with simply poking a multimeter into each pair of holes, but that would mean you have to try 29 plus 28 plus 27 and so on. Too much for my patience. Let's try to automate this process using a microcontroller such as an Arduino. An Arduino has a bunch of pins that can be configured to either be an input, so it tells you if they are connected to 0 volts or 5 volts by reading 0 or 1, or an output, so the pin either emits 0 volt, which is output 0, or 5 volt. So our first idea could be to connect Arduino pins to the dongle, like so, where we represent with switches if the pins are actually connected to the metal plate or not. And now we need to decide which pins to configure as an input or as an output on the Arduino, so that we can deduce from this which switches are closed in this picture and which switches are open. There are really a few cases that we have to consider. Between two pins there is either a connection or no connection, and each pin can either be configured as input, output 0 or output 1. So in total we have 12 cases. The cases where we write a value to an unconnected pin are not interesting. No information can be gained from that, but we also don't do any harm. What about the cases where we read from an unconnected pin? This will result in a random value, either 0 or 1, to be read. Basically picking up electrical noise. Not so great. Doesn't do any harm though, but doesn't give us any real information and might actually confuse us. How do we fix that? So take a look at the following circuit. We connect the pin that is represented here with a square to ground with a very big resistor. Now, if we read it with nothing else connected, we should get 0 because it's still connected to ground through this 10k ohm resistor. However, if we connect the pin to 5 volt, we still get a 1 because the current will take the path of least resistance. So it will flow from directly to the pin and not through the 10k resistor to ground. Note that we assume here that there is no, or at least much less than 10k ohm resistance on the input. But if the resistance on an input is low, that means if we connect a high output to an input, a lot of current will flow and damage the input. In fact, inputs have a high impedance, around 10 mega ohm in the case of the Arduino. Or maybe we just pull that pin to logic high instead, when it's not connected, like so. Now, if nothing is connected to the pin, it reads as logic 1. If we connect 5 volt to it, it also reads as logic 1, and the current flowing is still tiny. If we connect 0 volts to it, it will read as 0. Since this works so well, many microcontrollers come with built-in pull-up resistors. Often you can enable and disable them in software. Let's make sure to enable them and keep in mind that reading a 0 from an input either means the input is connected to 5 volt or not connected to anything. The cases where an input pin is connected to an output pin, regardless if that output 0 or 1, are also not a problem. This is exactly what input and output pins are designed for, right? The input pin will read the value that the output pin outputs. Now, the only cases left are those where we connect an output pin to another output pin. Connecting an output pin which outputs 0 to one that outputs 1 will destroy at least one of the two pins because a high current will flow between them. We have two options to avoid that situation by adding a resistor to every pin so that we limit this current, or simply remembering not to configure more than one pin as an output at any time. Let's go with the second option, since it saves hardware. Connecting two input pins together doesn't do any harm. We just need to remember that we will read both as 1 due to the pull-up resistor we decided to use. But if inputs read as 1, regardless if they are connected to a 1 output or not connected at all, how do we differentiate between these two cases? We can simply have our single output pin always output 0. Now every connected input will read 0, every unconnected input will read 1. By sweeping across all pins and making the output 0 one by one, we can uncover the entire set of connections. In code, this would look like something like this on the Arduino. Now we can try this out. If you have a real Arduino, compile the code and make some connections on pins 2 to 13. See how it identifies all the connections correctly. If you don't have an Arduino, there are simulators which let you play with a virtual one like Vocwi or Simulite. Now we can decode a dongle using a simple Arduino program. Well, not really. As I've shown you, the dongle has 30 holes, but a normal Arduino only has 17 usable pins. How can we get around this problem? One way to solve this problem is by using an I/O expander chip. Such a chip has two types of pins: I/O pins, just like an Arduino, and pins for communication via some kind of serial protocol. By sending commands via the communication protocol, we can configure the behavior of the I/O pins, making them into inputs or outputs. Also, connecting 30 cables to the dongle is not fun. Luckily, the connector of the dongle is just 3 by 10 pins with 2.54 mm spacing, so we can simply solder some 2.5 mm connectors to a perf board to emulate it. Or we could just find one of these connectors for less than $2 on AliExpress. All my previous projects were built on breadboards or perf boards, but the number of connections involved in this project made me think it was time to try to design my first PCB for manufacture. I found JLCPCB, which lets you order as little as 5 PCBs for a very good price, around $2 per board. And they even include an SMT assembly service, which means we can get the I/O expander chip from them as an SMD part and not worry about soldering that either. For designing the PCB, you have a couple of software options, such as Eagle, KiCad or Altium. However, JLCPCB also offers online tools for schematic capture and PCB layout, which allows you to directly import parts sold by them and also order the finished PCB, all from one tool. I think this is the most beginner-friendly option. So let's start designing our first PCB. I decided to use the MCP27017 chip for the I/O expander. This means we will need 2 of them to get a total of 32 I/O pins. This chip uses the I2C protocol or I2C protocol, so we only need 2 pins from our Arduino to connect to both I/O expanders. To distinguish different I2C devices on the bus, each of these devices needs an address. A part of the address of a device is set by the manufacturer of the chip, and a part, in this case the lower 3 bits, by the connections made to the chip. In our PCB, we connect the address pins either to VCC or ground to get 2 different addresses. The I2C clock and data lines need to be pulled high when not used, so we add 2 resistors to VCC. We connect the I/O pins of our 2 I/O expander chips to the 30 pins on the dongle connector. Doing this manually really annoyed me, and I would have wished there is a way to doing this programmatically. I would also like to have the ability to use this PCB in the future in other projects where a lot of pins are needed, so I decided to add a second connector which breaks out all the I/O pins of the I/O expander. And of course we need pins for VCC, ground and the 2 I2C bus lines, SDA and SCL. I added each of these pins twice to the secondary connector, so we end up with a nice round number of 40 pins. When laying out the PCB, I made sure everything is nicely labeled. And here I made my first mistake that I'm aware of. The labeling of the dongle pins will be completely covered by the dongle connector once it's soldered onto the board. Two other things I would have done differently. If I would have made the board slightly bigger, I could have designed it such that it directly plugs into an Arduino Uno, so there would be no need to connect any cables. And by making the address configurable, for example with jumpers, I could have allowed for chaining multiple such boards. Well, none of these are a deal breaker, and I'm happy that the first board I designed actually worked. About 2 weeks after ordering, the boards arrived and we can start writing the Arduino code to interface with them. The Arduino already comes with a library that implements the I2C protocol, but we still need to understand how it works to use it properly. I2C uses bus transactions, so if we want to send something from the Arduino to our I/O expanders, we use the begin transaction function from the Arduino I2C library, which takes the destination device address as an argument. Then we can use the write function to send one or more bytes to the device. We can see from the datasheet of the I/O expander that it expects us to send an address of 8-bit and then 8 or 16 bits of data. The addresses available are also explained in the datasheet. Let's give them some nice names in our code. For example, the first address can be written to decide the direction of the pin. That means if it should behave like an input or an output. There is another address to enable pull-up resistors on each pin, and so on. I wrote a function to write a byte to a specific address or register, as it's called in the datasheet. Since our I/O expander has 16 pins, there are always two addresses, one which applies to the first 8 pins and one for the pins 7 to 15. Of course, we need a similar function for reading, which simply returns 8 bits. Now we can write a function which configures all but one pins as input, which takes the index of the output pin. When doing this, I discovered I wired up the pins for the I/O expander in a weird way in the PCB. The first 8 pins go to the higher address and the second set of pins to the lower one. Well, not great, not terrible. We can fix that in our code. In the function itself, we iterate over the 2 chips in the outside loop, then over the 2 8-bit banks on the inside loop in reverse order. In the inner loop body, we set the values we want to output for the output pins. We can just set this to all 0. The I/O expander we are using has a cool feature. It can invert the values we are reading. Remember, we are using pull-up resistors, so reading a 0 means the pin is connected to an output, and reading a 1 means it is not connected. By using this feature, we can invert the values we read in hardware, so we get 1s for connected pins. Lastly, we enable the pull-up resistors. After each loop iteration, we shift our mask, which controls which pin is used as an output, by 8 bits. Similarly, we need a function to read all pins and return the value in 32 bits. We know the last 2 bits will always be 0 since our dongle has only 30 pins. A 1-bit here means that this pin is connected to the current output pin since we chose to invert polarity. Our main loop is quite simple. We just iterate over all bits, configuring always one of them as output, then reading back all the values and outputting the pairs which we find are connected. I have already tried this with multiple such dongles and it works perfectly.